Hello, Krasimir here, and I'm going to show you how to create viscous fluids with FumeFX 6. It's not Flip or SPH solver, but we'll use physics constraints to create a connection between particles that will emulate viscous forces within fluids. So in this scene we have this biscuit that we're going to pour chocolate all over, and we have a simple plane that's position is animated over this biscuit. So we're going to create the NodeWorks object in the scene. Oh, here it is. And for a start, we're going to create the generate on the surface node. We're going to generate surface on the emitter plane, and now we can hide this plane. We don't need it anymore. As you can see, it generates particles on the plane and send them upwards and generate them just only on the first frame. And we're going to need to generate particles as long as the pour is going on, so that's 100 frames, and we're going to use 200 particles in total, and we'll use the surface offset to emit particles on various distance from its emitter. This is a little bit too fast, so we're going to reduce a little bit this velocity and change the direction on the negative z-axis. This is just so we have initial velocities for particles, and later on when we add physics, we're going to use physics gravity to pull the particles as they collide with the biscuit towards the collision plane. And that's so much about the emission. And now we're going to add another tab. We're going to handle physics collisions. It's always a good idea to move to the first frame so the changes doesn't trigger resimulation. This tab can be renamed to whatever we want, so we'll just call it physics, and we're going to create the physics static collision node that will import the table, the plane, and the biscuit geometry into physics as static collision modes. Let's go to the parameters. Here we have the simulation group. That's the ID for all those objects for the physics engine, and you can define other groups that these groups are going to collide with. So we thought that this is easier than you have to select all the groups with all the names, so it's pretty easy to change the collision groups. And you can see that it asks, please select the solver. We'll select the solver as soon as we add all the collision objects. So we're going to get the group 1. Let's make it chocolate brown. Something like that. I call them Choco, and let's add physics object. So these particles are now imported into the physics engine, and we'll just now add the physics solver, and we're going to go back and select solver. For start, these particles are going to collide. We're going to name them group 1 and let them collide with physics group 0. So this is physics group 0 and collide with group 1. This is physics group 1 and collides with the group 0. this is a dynamic collider type because those particles are moving, and we'll use sphere geometry, but a little bit smaller, 0.1. We don't want them to bounce, and we'll increase static and dynamic friction, and we can maybe increase the contact offset. That's for the collision detection. And now let's see what happens. You see those particles are now colliding with the biscuit and the plane, and they're going upwards. So for this static collision, we're going to remove the bounce completely, and we can also increase static and dynamic friction. With these new settings, we have achieved that particles are sticking to the collision object, and they're slowly sliding along the geometry. That's much better than we had before, and it will be easier to achieve the viscous fluid type effect. Okay, now we need to create some constraints between those particles to keep them together. So one thing I forgot here to mention, that we need to add those particles to the physics objects only when the particles are created, not for each frame. So only when the particle is created is going to be pushed to the physics simulation engine. So this filter will just output new particles through this connection to the physics object that will add those particles to the solver. And we'll have to repeat this once again, create new Choco particle group, and now we're going to need to create a neighbors node. This is a very important node in this FumeFX Nodeworks network, because it provides you ability to create all kind of things. For example, in this case, we're going to search for particles that are close to the particle in search. So we're going to search within the same chocolate particles group, and we're going to search for a maximum of 100 neighboring particles that are closest to our particle that we're observing. So for each new particle, we're going to go through all the particles within the group and find 100 nearest particles. For those particles, when they're found, we're going to push them into a physics new joint. So they'll create new joint. Fibers and joints have separate group. In this case, it doesn't matter, this group, because we won't use it later, but let's call this constraint group, and those new joints will have the constraint group flag on them. And now this particle here, pin, is the particle we are searching for, and this particle is going to be the first particle from the new joint, and this particle will create joints with all the particles that are located around that particle. And now you can see, as soon as we've connected those two pins, the simulation it's a little bit slower. We can also visualize those connections, but there's going to be a lot of those connections, so I'm going to lower the particle amount so that you can see what's going on. So let's use display attributes, and let's say we're going to see physics solver distant joints. Here you go. So for each particle is connected with the neighboring particles. As you can see, it's a vast network of joints interconnections. So it takes some time to do all these computations. So we reduced the amount of particles so we can see how it's going here. Now, I mentioned that we're going to create gravity because, as you can see, our initial velocity is not enough to pull the particles along the biscuit. So the physics solver, we're going to use the gravity in the negative z axis, and now you can see the particles are sliding very nicely along the surface. When we increase the number of particles to what we had initially, there will be more particles and more connections, so the whole system will actually behave differently, as you can see. We can now go and create caches for our particles. We'll do meshing once we cache particles, because just changing the meshing will trigger the resimulation for the particles. So we're going to disable most of the channels on the export that we don't need, and we're going to leave velocity as we're going to need it for rendering meshed particles with Arnold and motion blur. Okay, now when the caching is done with more or less default parameters, let's see how it's looking. Now you see that those particles are basically sliding all over the surface. Now that's because each particle in physics is considered perfect sphere, and that perfect sphere in the contact with the surface will rotate, and we don't want those particles to rotate, so we're going to lock the angular motion for each particle. Furthermore, for this physics joint, we want them fibers to be constraints to be stiffer, and we want more damping for this viscous simulation. So I'm going to restart caching. For recaching, you don't need to change to interactive mode, where you're in cache mode and you click the export button. The system will internally switch to the interactive mode, do the caching, and then switch back to the caching mode. So now, with this set of parameters, we've got a better stickiness to the dough and behavior, but right now it seems that it's a little bit too much, maybe like a solid piece of carpet or something like that. So we need a little bit to change some parameters. As in the real world, particles and constraints largely influenced by the mass of particles. So heavier particles are going to put more strain on the constraint stiffness. So if we, for example, increase the, let's say, density of the particles 125 and see how it's going to look like. Okay, so now let's see what we got this time. And we have the particles flow nicely over the biscuit surface, covering it more or less uniformly. So it takes a little bit play with the particle density and the physics constraint or joint stiffness and damping, and the number of the neighbors that each particle founds and create connections for have a great impact on the outlook. Now we've got our particles done, so this is one part of our simulation, and now we have to mesh those particles. Now there are two ways you can do that. You can do that, for example, if you create another tab, or you can just put it down here, and you note that you'll get particles here and use the ISurf. However, this is going to work only when the interactive mode is enabled, which means you'll need to play with those settings for the ISurf during the simulation and cache everything through that. So now I'm going to create a new workspace, and we're going to switch to the newly created workspace and create the load particle cache node, which we'll use to load particles. So we'll use the load import track, not the load, because the load will replace all the particles in the workspace, and the ISurf that we're going to use requires the particles to be tracked. This node also has the create missing groups and channels, so each cache file contains the group names from the workspace, and they're automatically created here. However, we haven't selected for the caching of the group IDs for each particle, so that information is not available, and the particles will be loaded by default to the group 1. We can disable this and delete those groups and get the group 1 node and connect the ISurf. ISurf creates the particle group for its shape, and you can see it's a little bit too thick, so we're going to create smaller meshing. And union of spheres is really simple model, and Subritson will work the best for this case. Each meshing mode has its own set of options, and if you want a smoother surface, you can increase this threshold and, for example, generate a little bit thicker radius. For example, like 1 is going to cover all those, some of the gaps, but I think that the 0.8 and 4 work the best for this in here. Now to the rendering. Oops, it was 4. So for the rendering, you can open the Arnold render view and activate the render view. As you can see, ISurf will automatically generate motion blur out of the box without any issues. So we just need to assign some chocolate looking material to our NodeWorks node, and that's pretty much it for the rendering part. Of course, you can cache all the ISurf meshing to another cache and load those caches in the workspace too automatically, so you don't have to remesh each time. Thank you for watching this tutorial. I hope you learned something about creating physics nodes, collisions and fibers, as well as particle meshing and using the Arnold to render ISurf with motion blur, which is click and render. Thank you.